Hi, Grace here. Today is Tuesday, September 8th, and I want to talk about number 3 on today's merit worksheet. I have made a bunch of recordings that I then deleted because they weren't perfect, so this time we're looking just to get through the whole thing. So if it's not perfect, bear with me. So number 3 is all about matching functions to graphs and contours, and my general strategy is going to be to first match up the functions in the graphs and then match up the graphs to the contours. So I'm starting with matching the functions to the graphs. And when I do this, there's generally a couple strategies that I follow. One of the things I look at is setting x or y or z equal to a constant. Now, when I do this, let's say I set x equal to a constant, what this does is tell me how the graph behaves when I take a slice along the x-axis, when I take a slice that's parallel to the YZ plane. And similarly, if I set y equal to a constant, I'm going to get a slice along the y-axis that's parallel to the xz plane. And if I set z equal to a constant, I'll get a slice along the z-axis that will be parallel to the xy plane. And that's actually what gives me my contours, my sort of bird's eye view. So you can think of x and y as sort of being, instead of bird's eye view, looking directly on or looking directly to the side. And when I say I set them equal to a constant, for me, I tend to view it as, okay, it's just some constant. I'm not assigning a specific value, but you absolutely can assign a specific value. You absolutely can say what happens when I set x equal to 0, or when I set y equal to pi, or when I set z equal to 1. That is also a way of setting them equal to a constant. For me, I've been doing this for a while, and so I do tend to think of it just as a general constant, but either way is good. Another thing that I'm looking for is to look at the end behavior. And by that, I mean, what's happening as x and y are getting really, really big? What happens to z? What happens to the equation? What's the limit as x and y are going to plus or minus infinity? Is it going to be the same, whether it's plus or minus? As x and y get really big, does z get really small? Does it also get big? Does it get big but faster or not as fast? Is it bounded? By figuring out what's going on at these limits, I'm sort of looking at the edges of the graphs and deciding, okay, do these seem like they're going off in the appropriate directions? And then the other thing that I like to look for are special features, I'm going to call them. What is unique to this equation or this graph that's going to help me match them together? And so one of those will be, is it periodic? Because if it's periodic, I expect to see a sine or a cosine in my equation, something like that. Maybe a tangent if I'm feeling really adventurous. And in my graph, I'm expecting to get this sort of regular curve happening, or this very regular feature. And if it is it periodic in x or in y or in both, or maybe is it periodic in something else? Could be periodic in some equation between x and y. It could be periodic in the line x equals 2y plus 4. I don't know. But that'll show up in my graph depending on, do I see it repeating across the x-axis or do I see it repeating on sort of an angle? And if it is periodic, what's the amplitude? Does it change over time? Do my waves get bigger or smaller, or do they stay the same? So lots of these are there's lots of features to a periodic graph that I can think about. What should they be for my specific equation? In addition to looking at if it's periodic, I can also look about, is it symmetric? Is there some kind of symmetry going on? And if so, where is that happening? Based on the equation, should I be able to switch x and y? Because then I would expect a symmetry along the line y equals x. Can I replace x with negative x, in which case I should get a symmetry along the line x equals 0, or can I replace y with negative y, in which case I should get symmetry along the line y equals 0. So do I expect to see symmetries, and if so, where? I'm also going to look at if there are any domain restrictions. If my equation has like a square root or a log in it, then I expect that to affect my domain. I expect that if I have log, I can't put anything negative or 0 inside the log. And if I have anything with square root, I expect that I can't put anything negative inside there either. So it's possible that I should be blocking off parts of my domain, and that when I look at the graph, those pieces are missing. Those pieces are not present because I can't plug them into my function in the first place. I also might want to look at, do I see an absolute value sign? If I see an absolute value sign, then if you remember from previous calc courses that absolute value has this sort of V-shaped graph, I expect to get something like that even now. I expect to get a bounce and a crease where the absolute value meets, where it switches from being you put in a positive and you get a positive to where you put in a negative but you still get a positive because of the absolute value. And then finally for me, the last thing I'm going to look for is if the expression x squared plus y squared occurs somewhere in my equation. Because I might remember from previous calc classes, x squared plus y squared equals r squared gives the equation of a circle of radius r. And so if I see x squared plus y squared happen somewhere in the equation that I'm looking at, I expect to see circles somewhere in the graph. So these are my top 3 methods for trying to figure it out. None of them is better than any other one, and I'm going to kind of use a mix of them to try and now puzzle through which graph is which off of the Merit worksheet specifically. So let's get that going.